Tonight, we're going to explore one of the most unsettling problems in all of space travel. We know exactly how far the nearest star is. 25 trillion miles. We know how fast we'd have to go to get there inside a human lifetime. About a fifth the speed of light. We've designed the sail, we've designed the laser array that pushes it. We've picked the target planet. We know roughly what it's made of and how long its year is. On paper, the trip takes 20 years. And when the probe arrives, it doesn't stop. It can't. Every interstellar mission we have ever designed is designed to miss. The encounter lasts less than a minute. Then the spacecraft is gone, out the far side, into the dark. Still moving at a fifth the speed of light. And by the end of tonight, you're going to understand why stopping is harder than going, and why the brakes, not the engine, may decide whether we ever really reach another star.
If you find this kind of thing as unsettling as I do, take a second to subscribe and leave a like. It's a small thing, and it helps this reach the other people who lie awake on the same questions. And tell us in the comments where you're listening from tonight, and what time it is where you are. This whole story is about arriving somewhere. I like knowing where it arrives. Now, let's begin. Let's start with something we've already done. The date is July 14th, 2015. A spacecraft called New Horizons is 9.5 years into its journey. It has covered 3 billion miles since launch. It's about to pass 7,800 miles above the surface of Pluto, closer to that world than any object built by human hands has ever been, or is likely to be again. It is moving at 31,000 miles per hour. One number matters here, and it isn't the distance. It's the speed. During the closest approach, New Horizons is not talking to Earth. It can't. Pointing the antenna home means pointing the cameras away, and the cameras are the whole reason it's there. So the spacecraft goes silent and runs a script that engineers in Maryland wrote years earlier. It assumes everything will still be where they predicted. 900 separate observations sequenced in advance, executed by a machine 4.5 light hours from anyone who could help it. The window for the highest resolution images is about 30 minutes, and on the ground, nobody knows anything. A signal from Pluto takes 4.5 hours to cross the solar system, so the mission control room in Maryland is watching a clock, not a spacecraft. The flyby happens, completes, and finishes at a time when the light of it is still in transit. The team has to sit through the entire encounter without knowing whether the probe survived the encounter. The confirmation tone, a simple burst meaning the spacecraft is alive and has data, arrives 13 hours after closest approach. People in that room had waited 25 years for a beep. Think about what that means. 9.5 years of flight, 15 years of design and lobbying and funding fights before that. Careers built on this one pass. And the part where you actually see the thing, in real detail, lasts about as long as it takes to make dinner. And what it saw was nothing anyone had predicted. A plain of nitrogen ice the size of Texas, with almost no craters on it, which means it's being resurfaced. Mountains made of water ice, 11,000 feet tall. Layered haze in the atmosphere of a world that wasn't supposed to have much of an atmosphere at all. Every one of those discoveries came out of half an hour. Then it was over. New Horizons kept going. It had to. It was built as a flyby, and a flyby has one speed and one direction, and no second chances. The data came home slowly, 50+ gigabits of it, trickling back at a few kilobits a second. The stream stopped whenever the spacecraft had to maneuver, or whenever the ground antennas were needed by another mission. The last fragment of the Pluto encounter arrived at the Applied Physics Laboratory in Laurel, Maryland, on October 25, 2016, 15 months after the flyby itself. Put that in ordinary terms. The entire scientific harvest of the mission is about 6 gigabytes. That's less than one movie file on your phone. It took 1.25 years to deliver, at a rate slower than dial-up internet from the 1990s. Nobody involved considered this a failure. It's the best planetary flyby ever flown, and it rewrote a textbook. But notice what we accepted to get it. We accepted that the encounter would be a single pass. We accepted that we'd get one look, from one angle, at one moment in that world's history. Then we'd spend 15 months listening to the tape. New Horizons couldn't stop, and nobody expected it to. It was never built to. Slowing that spacecraft into orbit around Pluto would have required a fuel load the mission could never have launched. Everyone knew it from the first sketch. Now scale that same decision up by a factor of 4,000. Now, let's talk about the distance. Proxima Centauri is the closest star to the Sun, 4.25 light-years. In miles, that's 25 trillion. 25 with 12 zeros after it. Numbers that size stop meaning anything, so here's a handle. The distance from Earth to the Sun is 1 astronomical unit. Light takes about 8 minutes to cross it. Proxima is 268,000 of those. Voyager 1 is our benchmark for fast. It launched in September of 1977, and it's still going. The momentum it coasts on was stolen from Jupiter and Saturn nearly half a century ago. It moves at about 38,000 miles per hour, roughly 10 miles every second. Faster than any rifle bullet, continuously, for 49 years. Aim it at Proxima Centauri, and it would arrive in about 73,000 years. The detail that always gets me is this. Sometime this November, Voyager 1 becomes the first object humans have ever built to reach 1 full light day from Earth. 1 day. A radio command takes a full day to reach it, and another day to hear back. That milestone took 49 years. A light year is 365 times farther than a light day. The Voyagers aren't even the speed record. That belongs to the Parker Solar Probe, which whips around the Sun at about 430,000 miles per hour. It's the fastest thing our species has ever made move. Express that as a fraction of light speed, and you get about 0.06%. At that speed, Alpha Centauri is 6,500 years away. And Parker only goes that fast because it's falling. Once it climbs back out, the Sun takes the speed away again. So what about the ambitious stuff? The most serious interstellar mission concept actually sitting on a drawing board right now is called Interstellar Probe. The same laboratory that flew New Horizons is studying it. Its goal isn't another star at all. Its goal is 1,000 astronomical units in 50 years. Roughly 10 times as far out as the Voyagers have managed. The trajectory work suggests about 7 astronomical units a year, using a Jupiter slingshot and the biggest rocket available. At 7 astronomical units a year, Proxima Centauri is 38,000 years away. Not close enough. Not remotely. Not with anything we know how to build. There's one more record worth mentioning, because it shows how long this wall has been standing. In the mid-1970s, 2 German-American probes called Helios dove close to the Sun and hit about 44 miles per second. Half a century of rocketry later, nothing that leaves the solar system has done meaningfully better. The Voyagers still hold the outbound record, with hardware designed on drafting tables. For a trip that fits inside a career, inside a funding cycle, inside a human life, the arithmetic is brutally simple. 4.25 light-years in 20 years means a fifth the speed of light. 134 million miles per hour, roughly 7,000 times faster than Voyager 1. Here's a feel for that number, because it's easy to say and hard to hold. At a fifth of light speed, you cross the distance from here to the Moon in about 6 seconds. The whole gap that took Apollo 3 days, gone in the time it takes to read this sentence. Earth to the Sun takes about 42 minutes. Voyager 1's entire 49-year journey. Everything it has done since 1977, you'd cover in about 3 weeks. That number is where the trouble starts. Not because we can't reach it, because of what it does to the other end of the trip. Now, let's talk about why, because the reason isn't the one you'd expect. In 1903, a Russian schoolteacher named Konstantin Tsiolkovsky published an equation. It has governed every rocket ever launched, and every rocket that ever will be. It's short, it has 3 terms, and it is the most pitiless piece of arithmetic in engineering. The idea underneath it is almost insultingly simple. A rocket goes forward by throwing mass backward. To go faster, you throw more mass, or you throw it harder. But the mass you're going to throw in the final minute of the burn has to be aboard from the first minute. You have to carry it, which means you have to accelerate it. which means burning more fuel just to move the fuel. Every pound of propellant you add makes the ship heavier, which makes every pound less effective. The returns don't just diminish, they collapse. Tsiolkovsky's equation says your final speed depends on the logarithm of your mass ratio, the total launch weight divided by the empty weight. Logarithms grow slowly, painfully slowly. Turn that around and it says something worse. Your mass ratio grows exponentially with the speed you want. Here's the staircase. Suppose you want to go as fast as your own exhaust. That takes a mass ratio of about 3. Twice your exhaust speed takes about 7. 3 times takes 20. 4 times takes 55. 5 times takes 150. Every step up costs you nearly 3 times the ship. 10 times your exhaust speed needs a mass ratio around 22,000. 20 times needs 500 million. There's no cliff anywhere on that curve. No place where physics suddenly says no. It just keeps climbing until the answer stops being a spacecraft and starts being a number. Put that against real hardware. A good chemical rocket throws its exhaust out the back at about 2 miles per second. That's the best chemistry can do, and we've been within a few percent of the ceiling since the 1960s. Reaching a tenth of light speed on chemical propellant needs a mass ratio with more zeros in it than there are atoms out there. It isn't expensive, it isn't difficult, it's arithmetically impossible, and no amount of engineering touches it. Fusion does far better. A fusion drive that could channel its plasma cleanly out the back might throw exhaust at something like a 30th of light speed. Suddenly, the numbers behave. To reach a tenth of light speed with a drive like that, the mass ratio comes down to roughly 20. 20 pounds on the launch pad for every pound that arrives. That's heavy, but it isn't insane. Think of a car, where 19 of every 20 pounds you're hauling is gasoline. So far, this is just the cost of going. Now add the brake. Here's where the intuition fails almost everybody, and it failed a lot of professionals too. We'd all think stopping costs the same as starting. Same change in speed, same fuel, double the bill. It doesn't work that way. The propellant you'll burn to slow down at the far end has to be carried the entire distance. So it has to be accelerated to cruising speed along with everything else. The launch stage isn't pushing the payload up to speed. It's pushing the payload plus the entire braking system plus all the fuel the braking system will eat. And by Tsiolkovsky, pushing that much extra mass takes far more than twice the fuel. Run it properly and the 2 stages multiply. The mass ratio to get there times the mass ratio to stop, and both of them are exponentials. 20 becomes 400. The brake doesn't add to the bill, it squares it. Stay on that for a second. It's not a design flaw. There's nothing to optimize. It's a property of throwing mass backward in a vacuum, and it applies identically to chemical rockets, fission rockets, fusion rockets, and antimatter rockets. The only thing that changes is where on the curve you sit. And notice something about the shape of the problem, because it's going to matter all night. Going and stopping are not symmetric. They look symmetric. The change in speed is the same size. But the launch happens where we have factories and fuel depots and a whole planet's industry standing behind it. The stop happens 25 trillion miles from the nearest wrench. That single fact decided the design of the first serious Starship anyone ever drew. Now, let's look at what happens when engineers take that seriously. Between 1973 and 1978, about 11 scientists and engineers from the British Interplanetary Society sat down together. They wanted to find out whether an interstellar probe was possible at all. They met in their own time, in the evenings, unpaid. They called it Project Daedalus, and it was led by a former Rolls-Royce rocket engineer named Alan Bond. They set 3 rules, and the rules are what make the study matter. No invented physics. Relativity, yes. Fusion, yes. Anything that required a discovery, no. Second, the mission had to be completable inside 1 human lifetime, so the people who started it could theoretically live to see the data. Third, a real scientific payload, not a token camera. The target was Barnard's star, 5.9 light-years out, chosen because at the time it was thought to have planets. That part turned out to be wrong, incidentally, and then wrong again in the other direction. The 1960s evidence for planets around Barnard's star was discredited within a decade. The wobble in the data came from the telescope, not the star. Then, in the last couple of years, astronomers found real planets there after all. 4 of them, all smaller than Earth, all orbiting so close in that they're cooked. Daedalus was aimed at a system nobody understood, on the strength of a measurement that was already falling apart. Half a century later, it turns out there was something to see. Just not the thing anyone was looking for. What they produced is still the reference design half a century later, and it is enormous. Daedalus weighs 54,000 tons at departure. 50,000 tons of that is fuel. Deuterium and helium-3, frozen into pellets, detonated by electron beams at 250 pellets per second. A magnetic field channels the plasma into thrust. 30,000 tons of the helium-3 doesn't exist on Earth in useful quantities. So the study proposed mining it from the atmosphere of Jupiter with floating factories. Then it treated that as a solved subproblem and moved on. The scientific payload is about 450 tons. Look at the ratio. 50,000 tons of fuel to deliver 450 tons of instruments. 100 to 1. And that's the optimized version. It flies in 2 stages. The first burns for 2 years and reaches 7% of light speed, then drops away. The second burns another 1.8 years and tops out near 12%. Then the engines go quiet and Daedalus coasts for 46 years. Now here's the part people skip past when they see the pictures. Daedalus has no brakes. None. Not an underpowered braking system, not a partial one. The design contains 0 provision for deceleration, and that was a deliberate choice made early. The team ran the same squared mass ratio we just walked through. A version of Daedalus that could stop was not a spacecraft. It was a fantasy with a hull drawn around it. So they engineered around it. The ship would tear through the destination and never look back. 25 years into the cruise, telescopes aboard the second stage begin studying the target system from a distance, picking out objects worth a closer look. Between roughly 7 years and 2 years before arrival, the ship releases 18 autonomous subprobes. Each has its own ion drive. Each is aimed at a different target. They're called wardens. They fan out ahead of the mothership and take their own passes at their own objects. Everything goes back to the main vehicle, which relays it to Earth using its 40-meter engine bell as a radio dish. The front of the ship carries a 50-ton beryllium shield, 7 millimeters thick. At 12% of light speed, a grain of interstellar dust is a shaped charge. And ahead of that, the design calls for firing a cloud of particles 200 kilometers out in front. Anything larger gets detonated before the ship reaches it. All of that engineering, all of that shielding, all 18 wardens, for an encounter that lasts about 5 days. That is the honest number. A planetary system 100 astronomical units across, crossed at 12% of light speed, gives you roughly 5 days from edge to edge. The interesting inner part of it goes by in hours. 50 years of flight, 50,000 tons of fuel, a long weekend of science. No second pass, no orbit, no going back for the shot you missed, no adjusting the plan after the first surprising picture comes in. By the time you've seen the picture, the thing in it is behind you. And put yourself in the room where that decision gets made. You're an engineer in 1976. You've established that a Starship is buildable. You've solved the fuel, at least on paper. You've solved the shielding, the navigation, the autonomy. And then somebody asks the question about arriving. You run the numbers. You have to stand up in front of your colleagues and say, it works, but it can't stay. We can build a ship that reaches another star. We cannot build a ship that gets there. And then Daedalus is past it, still doing 12% of light speed, headed into empty space forever. It transmits the tape home for another decade while it recedes. Now, let's come back to the brakes, because 30 years later, another team decided that 5 days wasn't good enough. On September 30th, 2009, the British Interplanetary Society and the Tau Zero Foundation started a successor study. They called it Project Icarus. They wrote one new sentence into the terms of reference that changed everything. Deceleration at the target is a mission requirement. Not a stretch goal, a requirement. If it can't stop, it isn't a design. The team looked at reverse thrust first, the obvious answer, and rejected it for exactly the reason we've been building toward. Their own words, roughly. Assume an equal acceleration and deceleration profile, and the mass ratio scales as the square compared to a flyby, which requires an enormous amount of propellant. They called it a turnoff. Then they went looking at magnetic sails and nuclear pulse options instead. But even with the exotic options on the table, the requirement cost them. So here is the bill. Daedalus cruised at 12% of light speed. The Icarus fusion designs came in at 4.5 to 5%, less than half. Daedalus was a 50-year mission. Icarus is a 100-year mission. Double. Daedalus carried 450 tons of payload. Icarus budgeted 150, a third. They didn't fail to build brakes. They bought them, and that was the price. Half the speed, twice the duration, a third of the science, and the entire justification for going fast in the first place gone. Think about what doubling the mission time actually does to the people involved. On a 50-year mission, a graduate student who works on the launch might live to see the encounter data. On a 100-year mission, nobody does. Not the designers. Not the engineers who fix the software in year 30. Not their children. You are building a machine whose entire purpose will be fulfilled in front of an audience of strangers who haven't been born yet. The Icarus study wound down over the following years, and its final review was published only recently, in 2025. The conclusion is carefully worded, and the wording is worth hearing precisely. The study, it says, outlined credible pathways. A mainly fusion-based design could decelerate a large scientific payload into orbit around a nearby star in under 100 years of mission duration. Credible pathway. Not a design, not a blueprint. A direction in which a blueprint might one day be found, assuming fusion drives that nobody has built and mass ratios nobody has priced. That's where the rocket answer stands, after 50 years of the best people in the field looking at it. But there's another way to build a Starship, and it showed up in 2016 with $100 million behind it. In April of that year, a Russian-born investor named Yuri Milner held a press conference in New York. It was at the top of the rebuilt World Trade Center. Stephen Hawking was on stage. Freeman Dyson was on stage. The plan was called Breakthrough Starshot, and its central idea is beautiful. Leave the engine at home. Every problem we've talked about comes from carrying your propulsion with you. So don't. Build the engine on the ground, where it can weigh as much as it likes, and shoot the energy at the spacecraft. The hardware works like this. On a high, dry mountain site, you build a phased array of lasers roughly 6 miles on a side. Individually, the lasers are ordinary. Phased together, so their light waves line up. They act like one aperture a kilometer wide. Total output, 100 gigawatts. That's about 4 large power stations, all firing at once, at a single target in space. The target is a sail 4 meters across, a few hundred atoms thick, weighing 1 gram. Attached to it is a chip, also about a gram, with cameras and a laser transmitter and a nuclear battery. The beam fires for roughly 10 minutes. Photons have no mass, but they do carry momentum, and a 100-gigawatt beam, perfectly reflected, pushes with about 667 newtons of force. Against a rocket that's nothing, less than the thrust of a small jet engine. Against something that weighs as much as a paperclip, it's a hammer blow. The sail experiences roughly 40,000 times Earth's gravity, sustained, for the length of that burn. 10 minutes later, it's doing a fifth the speed of light, and it's already past Mars. 20 years after that, it reaches Alpha Centauri. Now, imagine building something that has to survive that. 40,000 gravities means a 1-gram chip momentarily weighs about 88 pounds, distributed across a membrane thinner than a soap bubble. It has to stay reflective, or it absorbs the beam and vaporizes. It has to stay flat, or it slides off the beam and tumbles. The leading candidate material is silicon nitride, and engineers have assembled it at the millimeter scale, but not the meter scale. The laser is worse. A single laser that powerful doesn't exist and can't be built. So you combine thousands of ordinary ones and phase them. Teams have now demonstrated that in a laboratory with a few dozen lasers, Scaling that to a working array means correcting for atmospheric distortion in real time. A reference beam fired continuously into the sky acts as the guide. The array has to be adjusted millions of times every second. The project's own summary named that as possibly the single largest technical hurdle in the whole program. And then there's the price. Powering that array at current laser costs runs around $100 per watt. For Starship to be affordable, one of the participants estimated, that number has to fall to somewhere between 1 and 5 cents, a factor of a few thousand. There's a quieter problem too, which nobody at the press conference mentioned. A 100-gigawatt phased array that can throw energy at a target in space is, by any reasonable definition, a weapon. The research that inspired the whole concept came out of a conference on shooting down missiles. Building one requires a level of international trust nobody currently has. At founding, the project identified around 30 problems that had to be solved before any of this could happen. 4 of them got sustained attention: the sail, the laser, the chip, and the communications link back to Earth. Look at that list again. The sail, the laser, the chip, the radio. All 4 are about going. Deceleration was never one of the 4, and the project's own scientists were blunt about why. Avi Loeb, one of the leads, put it plainly. Slowing down and entering orbit at Proxima would obviously be a huge benefit. There is no way to make it happen on a payload that has to weigh a gram. The first interstellar efforts, he said, will be flybys for that reason. The project is now on indefinite hold. There was no announcement. The meeting stopped, the funding stopped, and the executive director eventually confirmed by email that the program had been paused and portions transitioned elsewhere. Of the $100 million, most never materialized. One participant totaled up the actual spending at roughly $4.5 million across about 30 contracts. So a decade of serious work by serious people ended without ever budgeting a single dollar for the problem of arriving. We need to talk about what that arrival actually looks like. The numbers have gotten more precise since Starship went quiet, and they are worse than you'd think. The current best-developed version comes from a design study published this spring. Instead of one probe, you send a swarm. 1,000 of them, launched over a few weeks. Each weighs 3.5 grams. Each is a disk 4 meters across. They fly edge-on for most of the journey, presenting the thinnest possible profile to the interstellar wind, with an armored rim taking the erosion. The study assumes that 70% of them will be lost along the way, to dust, to radiation, to sheer bad luck. 300 arrive. At 1/5 of light speed, the swarm covers 60 meters every microsecond. One blink, and it has crossed 4 times the width of the United States. The approach begins about 8 days out, when a few probes turn their instruments forward and start filming. They accept that pointing their optics into the wind will destroy them. 14.5 hours before the encounter, from 21 astronomical units, the planet stops being a point of light and becomes a disk. Then it's on top of them. The close flyby of Proxima Centauri b lasts less than a minute. Say that number out loud, because it's the whole video in one line. The nearest potentially habitable world outside our solar system, 4 light-years away, 20 years of flight, and the visit lasts less than a minute. At closest approach, a single camera aperture manages something like 2 to 4 full exposures. Not 2 to 4 minutes of video, 2 to 4 pictures. Everything else has to be stacked out of severely underexposed microframes, a millionth of a second long. Anything longer smears. The swarm records terabytes doing it and can't send them. The link home carries about 900 bits per second, roughly 3.5 gigabytes a year, which is about the same as what New Horizons sent back from Pluto. The same data budget, from 4 light-years instead of 3 billion miles. So the probes have to choose what to keep, autonomously. 4 light-years from anyone who could advise them, weighing which photograph of another world is worth the bandwidth, and throwing the rest away forever. The designers have a name for the way this goes wrong. They call it the tourist problem. Send 1,000 people to a famous city. Hand each of them a camera and tell each of them to pick their single best picture. You get back 1,000 nearly identical photographs of the same landmark. So the swarm has to talk among itself, compare candidates, and agree on which images are worth the light. All while flying apart, on a radio link between neighbors that runs at 10 kilobits. That's the mission. 300 surviving machines, holding a committee meeting about a planet, in the dark, and then broadcasting the minutes home for a year. Now hold that image and ask the obvious question. Why not just slow down? Consider the physical size of what you'd be asking. A single gram, moving at 1/5 of light speed, carries about 1.8 trillion joules of kinetic energy. Convert that into something you can picture, and it comes out to roughly 400 tons of TNT. 400 tons in 1 gram, in a machine that weighs less than a paperclip. That's not a figure of speech about how impressive the speed is. That's the invoice. Any break of any kind has to take 400 tons of TNT worth of energy out of that object and put it somewhere else. And scale up to a real spacecraft. 1,000 tons of payload at 1/10 of light speed carries close to what the entire human species uses in 9 months. So what's available to absorb it? Your instinct says gravity. Stars are heavy, let the star catch it. It won't. Not by a margin anyone would call close. Whatever stops it, it will not be the star. So let's start working through the ways to stop, one at a time. There are about 10 that anyone has ever seriously proposed, and we're going to walk through every one of them tonight. So, the first. Braking scheme number 1 is the one everybody thinks of, and it's the one we already know how to build. Turn the ship around and fire the engine. Mechanically, it's the simplest thing in the world. Somewhere in the outer reaches of the target system, the spacecraft rotates 180 degrees. The drive lights. Instead of pushing you forward, the exhaust now streams out ahead of you. The ship sheds speed at the same rate it once gained it. Do it long enough, and you arrive at rest, hanging in the target system. Free to maneuver. Free to enter orbit. Free to look at that planet for 30 years instead of 40 seconds. It works. There's no physics objection at all. This is not one of the schemes that fails on some subtle effect nobody anticipated. It fails on arithmetic, in the first line of the calculation, and it fails the same way every time. Take the most generous case anybody has published. Assume a fusion drive that converts about 0.7% of its fuel mass into energy. That's the theoretical yield of hydrogen fusion. Then assume you capture nearly all of it and direct it backward with no losses. That's not a design. That's the ceiling. With that drive, reaching 1/8 of light speed takes a mass ratio of about 2.9. Under 3 pounds on the pad for every pound that gets there. That's better than a Falcon 9. Now stop as well as start, and the ratio becomes 8.4, which sounds fine. It's the number that gets quoted when someone wants to argue that interstellar flight is tractable, and it's easy to see why. 8.5 to 1 is a rounding error compared to what we tolerate getting to orbit. But notice what's buried in it. That figure assumes a perfect fusion rocket. Nobody has built a fusion rocket. Nobody has built a fusion reactor that produces net power for more than a few seconds. Not on the ground, with a building full of engineers standing around it. So take that ceiling and back off it. Suppose the real drive throws exhaust 1/3 as fast as the ideal, which would still be a staggering achievement. The exponent triples. The one-way ratio climbs from 3 to about 28. And the round figure, the one that includes the brake, goes into the thousands. Thousands of tons of frozen fuel per ton of instrument. And this is where the questions start piling up faster than anyone can answer them. What do you tank it in? What keeps deuterium at 400 degrees below 0 Fahrenheit? That's 240 below in Celsius for 100 years with no resupply. What happens to a weld that's been holding cryogenic pressure since before your grandparents were born? What happens to insulation after a century of cosmic rays? What breaks first, and who's aboard to notice? Nobody knows. Not one of those questions has a published answer, because the studies don't get that far. They stop at the mass ratio, because the mass ratio has already ended the conversation. And here's the version of it you can feel in your body. Imagine loading a car for a drive across a continent, except there are no gas stations anywhere, in either direction, and there never will be. Every gallon you'll burn coming home has to ride with you the whole way out, which makes the car heavier, which means burning more on the way out, which means loading more for the return. Now do that same problem where the trip is 25 trillion miles long and the fuel has to stay frozen for a century. That's not an engineering challenge. That's a shape. The shape doesn't care how clever you are. And there's a turn of the screw underneath all of it. Every pound of that brake has to be pushed up to cruising speed at the beginning of the journey. The equation feeds on itself. Add braking capacity, and you've added something that needs braking. Nobody has found the bottom of that loop. There isn't one. So we take the fuel out of the ship, all of it. If the brake can't be carried, then whatever stops us has to be out there already, waiting. And the first candidate is the oldest one there is, gravity. This is braking scheme number 2, and almost everybody reaches for it. We've done it dozens of times. Voyager 1 got its speed from Jupiter. New Horizons picked up 9,000 miles an hour at Jupiter and cut 3 years off the trip to Pluto. Nobody burned fuel for that. We stole it. So why not run the trick backward and steal the speed away again at the far end? We can. It just doesn't help. Here's the mechanism, and it's worth going slowly because the intuition fails in a specific way. Flying past a planet, we fall in and we climb out. Falling in, we gain speed. Climbing out, we lose it. The path is a hyperbola, and a hyperbola is symmetric. Measured against the planet itself, we arrive at some speed, and we leave at exactly that speed. The direction changes. Nothing else does. You felt a version of this. A car in neutral rolls down one side of a valley and up the other. It reaches the far crest, doing almost exactly what it was doing at the first crest. The hill gave back everything it took. Space is that valley without the friction. So where does the free speed in a gravity assist come from? Not from the planet's gravity, from the planet's motion. Jupiter is moving around the Sun at about 8 miles per second. Bend a path against that motion, and we borrow a sliver of Jupiter's orbital energy. Jupiter loses an amount too small to measure. The bookkeeping only balances because there are 3 bodies in the problem, and the third one is the Sun we already orbit. Now put that in the context of arriving at another star. We come in from interstellar space. There is no third body. There is nothing we're already orbiting. Relative to that star, whatever speed we bring in, we take back out. Every mile per second the star's gravity strips off on the way in, it hands straight back on the way out. A flyby cannot capture anything. It never has. Gravity only holds on to an object that arrives slower than escape velocity. The question becomes what escape velocity actually is around real bodies. The numbers are humbling. Jupiter, the heaviest planet we've got, holds on at 37 miles per second. That sounds enormous. At 37 miles per second, you'd cross from New York to Chicago in about 20 seconds. The Sun holds on at 384 miles per second, measured right at the surface of the fire, coast to coast across America in a little over 7 seconds. It is the strongest grip an ordinary star can apply to anything. 0.2% of the speed of light. Our probe arrives at 1/5 of light speed, 100 times faster than the fastest thing a star can hold. Catching it with gravity is like stopping a car with a strip of tape. And it's worse than that, because escape velocity falls off with distance. To use even that much, we'd have to graze the surface of the star. Out where a habitable planet sits, the grip is feebler again by orders of magnitude. We're not asking to be caught by a star. We're asking to be caught from 4 million miles away, at 1/5 of light speed. It isn't close. There's one loophole, and Alpha Centauri actually offers it. 2 stars orbiting each other do give you a third body. Threading between them, an incoming object can lose energy to the pair and end up bound. Astronomers see it happen with comets around Jupiter. The catch is the entry speed. That trick only works on something already crawling, at roughly the speed the 2 stars orbit each other. For Alpha Centauri A and B, that's about 10 miles per second. So the loophole exists. It's just 3,000 times too slow to be any use to us. 2 other versions of this come up, and both deserve an answer. The first is the Oberth maneuver. It's real, and mission designers use it constantly. Fire your engine deep inside a gravity well, moving fast. Each pound of propellant then buys far more energy than the same pound would buy out in the open. Diving toward a star and burning at the bottom is very efficient. But look at what it requires. An engine, propellant, the thing we just removed to get here. The Oberth effect makes a rocket better. It doesn't make a rocket unnecessary, and we already know what the rocket costs. The second is aerobraking, and we rely on it. Spacecraft arriving at Mars dip into the upper atmosphere over and over, shedding speed for free until the orbit tightens. It's elegant, and it costs nothing but nerve. The problem is what air does at these speeds. A returning space shuttle hit the atmosphere at about 5 miles per second. The leading edge of its wing reached 3,000 degrees Fahrenheit, roughly 1,600 Celsius. That's from thin air, at a speed we consider routine. Arriving at another star, we'd be moving 7,000 times faster, and the energy involved rises with the square of the speed. Anything dense enough to slow us at a fifth of light speed doesn't slow us. It converts the ship into a cloud of glowing gas inside the first tenth of a second. 400 tons of explosive in a machine you could lose in your pocket. Nothing made of matter absorbs that gently, so the destination can't help. Not the star, not its planets, not their air. Which leaves us asking the people who launched us to keep pushing, from 25 trillion miles away. Breaking scheme number 3 comes from a physicist named Robert Forward, working at an aerospace research lab in California. He publishes it in 1984, and it is still the most ingenious thing on this entire list. Forward starts where we did. The engine stays home. A laser on our side of the gap pushes a sail. Fine. But now the sail is out there, and the light is coming from behind it. Light from behind can only push you forward. To slow down, you need light arriving from in front, and there is nothing in front. So Forward builds the thing in front out of the sail itself. Take this slowly. The sail flies out as 2 nested pieces. There's an inner disc carrying the payload, and around it a much larger ring, joined at the rim. For most of the journey, the two travel as one object, riding the beam. Then the target comes up. The inner disc lets go. It drops back slightly, rotates 180 degrees, and turns its mirror face back the way it came. The beam from home arrives. It passes the payload disc and strikes the ring. The ring is shaped so it doesn't reflect the light straight back. It focuses it, forward and inward, onto the payload sail from ahead. The ring accelerates away and sails past the star forever. The payload, now taking light on the front of its mirror, slows down. One beam, one laser, both jobs. Nothing has to be built at the destination. On paper it works. Now the numbers, and this is where the evening turns. Forward's flyby version is modest by Starship standards. A 1-ton probe, a sail 2¼ miles across, a 65-gigawatt laser. It reaches 11% of light speed and passes Alpha Centauri 40 years after launch. The version that stops is a different animal. The payload sail grows to 19 miles across and 71 tons. Around it goes the decelerator ring, 62 miles from rim to rim, weighing 710 tons. Stand one edge of that ring on the ground, and the far edge is well past your horizon. Weigh those two numbers against each other. 10 pounds of mirror for every pound of instrument. The brake isn't part of the ship. The brake is the ship, and the science rides along as cargo. The two launch together and coast at 21% of light speed. Then, on approach, the braking beam comes on. 26 terawatts, 65 gigawatts to fly past, 26 terawatts to stop, 400 times. For the same distance, to the same star, carrying the same instruments. Let that land properly. 26 terawatts is more power than our species currently uses. Every power plant, every engine, every furnace, every light bulb on Earth, running at once, adds up to about 20 terawatts. Forward's brake needs more than all of it, aimed at one mirror, and it needs it for years. And we haven't built the lens yet. Holding a beam tight over interstellar distances takes an aperture enormous enough to fight diffraction. Forward's answer is a Fresnel lens 620 miles across. Concentric rings of transparent film, held apart by spars, floating permanently somewhere between the orbits of Saturn and Uranus. 620 miles is a full day of hard driving, edge to edge. It has to hold its shape and its aim for a century. The pointing requirement was later summed up in one line that's hard to shake. The beam has to be delivered to the accuracy of a 100-kilometer sail at the far end of a 1-trillion-kilometer runway. Then there's the delay. Light takes over 4 years to cross that gap. So we don't aim at the ship. We aim at where the ship will be in 4 years, based on a prediction. Then we hold the beam there. We won't learn whether we missed until 8 years after we started. Picture holding a flashlight steady on a coin. The coin is in another city. You have to keep the beam on it for a decade without wobbling. If your hand slips for an afternoon, you find out about it years later, from a machine that is by then unreachable. And Forward went further, because he wanted people aboard. His round-trip design carries a crew to Epsilon Eridani, 10.8 light-years away. The sail is 1,000 kilometers across. Total vehicle mass, 80,000 tons, of which 3,000 tons is crew and equipment. The sail splits, not into 2 stages but 3, so that after the crew finishes exploring, a smaller ring can throw them home again. The laser system for that mission runs at 75,000 terawatts, not 26, 75,000. Something close to 4,000 times everything humanity currently generates, sustained for years. All of it to bring 3,000 tons of people to a stop, and then start them moving again. 2 engineers, Dana Andrews and Robert Zubrin, went through Forward's deceleration stage carefully a few years later. Their conclusion was blunt. That ring mirror has to hold its surface quality to a tolerance nobody considers plausible while flexing under the beam. And the beam's own steadiness would have to be far better than anything ever built. Forward knew. In the conclusion of his own paper, he named the pointing problem as a major unstudied issue and left it standing there. Maybe the answer is simpler. Instead of shipping light across the gap, let the destination supply it. There's a star at the far end. Stars make light. Breaking scheme number 4 says, turn the sail around and let the star we're arriving at do the pushing. It's the first idea on this list that comes with a real trajectory attached. It was published on the 1st of February, 2017, by an astrophysicist named René Heller and a colleague, Michael Hipke. The mission it describes is the most vivid thing in this whole subject. Here's how it goes. The craft is a sail of graphene with a reflective coating. About 1,000 feet on a side, roughly 1/5 of a mile. It carries a payload of a few grams. Sail and payload together weigh less than a deck of cards. It doesn't launch on a laser at all. It falls toward our own sun, comes within about 5 solar radii, and lets sunlight throw it out of the solar system. The sun is the cannon. The target star will be the wall. 95 years later, it reaches Alpha Centauri A. The maneuver itself. The sail turns face on to the oncoming star and takes the light on its mirror. Photons carry momentum, and the flood of them pushes back. At the same time, the star's gravity pulls the craft into a curve. Radiation pressure slows it. Gravity turns it. Together, they bend the trajectory into a hook. The deceleration during that pass runs to about 1,000 times Earth gravity, which is gentle by the standards of this field. A laser-riding sail takes 10,000. And it works at exactly 1 speed and no faster. The ceiling is 4.6% of light speed, 8,600 miles per second. At that speed, you'd cross from here to the moon in under half a minute. Arrive 1 notch quicker, and the star cannot turn the sail hard enough. It sails through and out and is gone. To get even that much braking, the pass has to come within about 2.5 million miles of the star, 10 times the distance to the moon, which sounds like a lot until you remember what's sitting at the middle of it. At that distance, the star's outer atmosphere runs above 180,000 degrees Fahrenheit, about 100,000 Celsius. The filament in an old-fashioned light bulb glows at around 4,500 degrees. This is 40 times hotter, and the sail has to sit in it for hours. The one mercy is the reflectivity. If the coating bounces back 99.999% of the light, the sail absorbs only about 24 watts per square meter. It settles at a temperature well below freezing. Lose a single 9 off that figure, and the absorbed heat goes up tenfold. The design needs 5 nines of reflectivity on a membrane a fifth of a mile wide. After 95 years in interstellar space, the heat isn't the real hazard anyway. Light we can reflect, plasma we cannot. Then comes the part that makes this the best story in the field. Alpha Centauri isn't one star, it's 3. A and B are a close pair, one a little brighter than our Sun, the other about half as bright, circling each other. Proxima is the third, drifting nearly 13,000 astronomical units out from the other two. So the sail breaks at A and comes out slower, pointed somewhere new. A few days later it reaches B. It breaks again. Now it's slow enough, and aimed correctly, to fall toward the third star. 46 more years of falling. About 140 years from launch, the sail arrives at the planet, moving slowly enough to stay. There's the payoff, and it's real. Now the price. You'll have noticed the route goes to the wrong stars first. Alpha Centauri A and B are farther from us than Proxima is. So why not go straight to the planet we actually care about? Because Proxima is faint. It puts out about 1/1500th of the Sun's energy. Stand the same distance from each, and it's a nightlight beside a searchlight. There aren't enough photons coming off it to stop anything. Run the numbers, and Proxima on its own can absorb about 800 miles per second. That's all. To break at the planet we came for, we'd have to arrive no faster than that, which means the journey takes roughly 1,000 years. Sit with that, because it's the shape of the whole problem in one fact. We can arrive fast and fly through in under a minute. Or we can arrive able to stop and take 40 generations to get there. The people who launched it and the people who received the first picture would not share a single word of the same language. There's an asymmetry buried in this that took me a while to notice. Alpha Centauri A and B, working together, can absorb an arrival speed of about 17,000 kilometers per second. But our own Sun, used as a launcher, can only throw the same sail out at about 11,500. The far end can take more than our end can give. The braking capacity isn't the binding constraint here. Our departure is. Which means a laser at home and photon braking at the target aren't rivals at all. They're two halves of the same mission, and nobody has costed the pair together. And the maneuver has one more constraint, and it's a strange one. It works best when all 3 stars happen to lie close to the plane of the incoming sail. That geometry comes and goes as they orbit. So there are launch windows, and they aren't measured in weeks the way a Mars window is. They're measured in decades. If you've stayed with me through the mass ratios and the mirrors and the corona, please subscribe and leave a like. It helps more than I can tell you. So let's stop using light altogether. There's something else out there between the stars, and it isn't nothing. Interstellar space is thin, but it isn't empty. Drifting through it is hydrogen, mostly stripped of its electrons, mostly moving slowly. In the cloud our solar system currently sits inside, there's roughly 1/10 of a particle per cubic centimeter. Here's what that means in something you can hold. Take a sugar cube. A sugar cube of the air in your room contains about 25 billion molecules. A sugar cube of interstellar space contains, on average, about 1 atom. That's what we're going to break against. Breaking scheme number 5 says it can be done. The idea is the magnetic sail, from Dana Andrews and Robert Zubrin in 1988. There's no sheet of material at all. Instead, we unreel a loop of superconducting cable and run an enormous current around it. That current makes a magnetic field, and the field reaches out for hundreds of miles in every direction. Tearing through the medium, we meet protons head-on. They can't cross magnetic field lines easily, so they curl and get thrown aside. Every proton deflected pushes back on the loop that deflected it. Multiply by how many we meet per second at a fifth of light speed, and there's a real force. What makes this the most attractive idea on the list is what it doesn't need. No propellant, no beam, no mirror, nothing waiting at the destination. A loop of wire, a current, and the galaxy. The current is the problem. To bend a proton arriving at relativistic speed, the field has to be violent. The number that comes out is around 1,000,000 amperes. The wiring behind the wall of your house carries about 15. A lightning strike peaks near 30,000 for a few millionths of a second. This loop has to hold 1,000,000, continuously, for decades. The cable itself is most of the spacecraft. Modern superconducting tape can carry 1,000,000 amps at a cost of about 1/3 of a pound per yard. To do it, the cable has to stay near 30 degrees above absolute zero. Deep space at least supplies the cold for free. For 30 years, Zubrin and Andrews' numbers were the numbers everybody quoted. Then people checked them properly. In 2017, a theoretical physicist named Claudius Gross simulated individual protons flying through the field of a current loop, one at a time. He measured how many actually turned around. What he found was not a gentle fall-off. Below a certain current, for a given speed, the effective reflecting area of a magnetic sail doesn't shrink. It vanishes. The protons pass straight through the field as though it weren't there, and the break stops existing. And the craft Zubrin and Andrews proposed for a tenth of light speed carried 159,000 amperes. It sits precisely at that boundary. Separately, a reanalysis done for Project Icarus found their drag figures optimistic by a factor of about 3. So what does an honest magnetic sail look like? Take a probe cruising at a tenth of light speed, aiming to reach Proxima Centauri in 58 years all in. The loop has a radius of 1,000 miles, 2,000 miles from rim to rim. The whole craft weighs about 1,500 tons, which is roughly 1,000 family cars, and nearly all of that is cable. The braking distance is 1/3 of a light year. The brake starts 1/3 of a light year out. The brake is the last third of the trip. 2 trillion miles of slowing down, 19 years of it. We begin braking where the destination star is still just the brightest dot in the sky. We finish nearly 2 decades later. Stretch the mission to 100 years instead of 58, and it eases considerably. The loop comes down to a radius of 270 miles, and the mass to 400 tons. Time is the only currency that ever buys anything here. The route matters too, and this is the part that surprised me. That figure of 1/10 of a particle per cubic centimeter is for the warm local cloud we happen to be sitting in. Out in the emptier stretches of our neighborhood, the density drops to 5 thousandths, 20 times thinner. The break depends on which way you go. Point the ship at one star and the medium is thick enough to work with. Point it at another and there's next to nothing to push against, and the same hardware is dead weight. One thing does come free with the loop, and so little else on this list gives anything back that it deserves a line. That same magnetic field deflects cosmic rays. A magnetic sail big enough to break a crewed ship is also the radiation shield that crew would need for the entire voyage. It takes no extra hardware to do it. The brake and the armor turn out to be the same object. There's a nastier detail underneath all of it. The magnetic sail works best when we're fast, because that's when protons come at us hardest. As we slow, the brake weakens, which means the great majority of the braking happens in the regime where the thing barely functions. But there's another kind of sail, and it works exactly where the magnetic one gives up. Braking scheme number 6 is the electric sail, proposed by a Finnish physicist named Pekka Janhunen in 2004. Instead of a magnetic field, we unreel long, thin wires and hold them at a high positive voltage. Some of these designs call for tethers 12 miles long, thinner than a human hair. Protons coming at us are positively charged, so they get shoved aside electrostatically. Every shove pushes back. The electric sail is poor at high speed and good at low speed, the exact inverse of the magnetic sail. It also does better close to a star, where the stellar wind thickens the medium considerably. The obvious move is to carry both and use them in sequence. In 2016, Nikolaos Parakis and Andreas Hein worked out what that buys. Their test case is a spacecraft weighing 8,250 kilograms, about 18,000 pounds, roughly a loaded delivery truck. It arrives at 5% of light speed and needs to come down to ordinary planetary speeds. With the magnetic sail alone, 40 years of braking. With the electric sail alone, 35. With both, in sequence, 29. 29 years. 3 dogs' lifetimes, one after another, spent slowing down. Good news, and a real improvement. Now here's the finding underneath it that nobody talks about. They also tested what happens if we simply build a bigger brake. Take a 4,000 kilogram craft coming in at 8% of light speed. Give it a braking system 10 times its own mass, and the job takes about 54 years. Cut that brake down to 4 times the craft's mass, less than half as much hardware, and the job takes about 56. Increase the brake by 150%, and we buy under 4%. We can't buy our way out. Past a certain point, the brake stops caring how heavy it is. And every extra ton has to be hauled up to cruising speed at launch, where we already know what that costs. The team behind that work, a study called Project Dragonfly, assembled the whole architecture and wrote down what it would buy. With a 100-gigawatt laser and both sails, they could deliver 250 kilograms of scientific payload to Alpha Centauri inside 100 years. About the weight of 3 grown men, arriving a century after launch. Their own written conclusion was that this is only enough to satisfy parts of the science goals. In their words, it renders the usefulness of such a mission questionable. 100 years of work, a quarter ton of instruments, the people who built it long dead, and their assessment was that it might not be worth doing. There's one more idea. Braking scheme number 7, and it was supposed to be the answer to everything. In 1960, a physicist named Robert Bussard published a paper that broke the rocket equation in half. His idea was this: if we can't carry the fuel, we gather it as we go. The medium isn't empty. So we fly a magnetic funnel out ahead of the ship and let it scoop hydrogen out of space. Compress it, fuse it, throw it out the back. The mass ratio disappears. There isn't one, because we launch with no fuel at all. And the faster we go, the more hydrogen we sweep up every second. In principle, the ramjet accelerates forever and never stops. Everybody wanted it to be true. It's the engine behind a shelf of novels. One of them turns entirely on a ramjet crew who lose the ability to slow down and just keep going. Generations of physicists say Bussard's paper is why they went into the field. Then, people checked it. In 1978, Thomas Heppenheimer worked through the radiation losses. Compressing hydrogen hard enough to fuse it makes it radiate furiously. The light pouring out of that compressed plasma dwarfs the power the reaction produces. Others found workarounds using different fusion cycles, and the argument ran back and forth for years. Then, in 1985, Andrews and Zubrin ran the scoop itself. And the scoop that gathers the fuel produces more drag than the engine produces thrust. Read that again. The intake is a magnetic field pushing against the interstellar medium. It slows the ship more than the fusion it feeds can speed it up. Not marginally, not in some edge case, in general. Nobody set out to design a brake. They designed the most famous Starship engine of the 20th century, ran the numbers, and found that it only works in reverse. That's where the magnetic sail came from, incidentally. Zubrin and Andrews were standing in the wreckage of the ramjet and noticed what they had instead. The scoop keeps getting bigger the longer anyone looks. Take a perfect ramjet, with no radiation losses and no drag at all. It would still need an intake hundreds or thousands of miles wide to manage 1/10 of a meter per second squared. That's about the acceleration of a car pulling out of a parking space. One recent analysis concluded that building a useful one would be beyond a civilization that had learned to harvest an entire star. Now, let's look at braking scheme number 8, the one on this list that actually closes the arithmetic. In 2020, an accelerator physicist named Gerald Jackson submitted a proposal to NASA's Advanced Concepts program. He'd spent years working on antimatter at Fermilab. The title of the proposal is worth hearing exactly. It's called the Deceleration of Interstellar Spacecraft Utilizing Antimatter. Notice what that title is. Every other proposal we've walked through tonight is a propulsion concept with a brake bolted on afterward. This one is a brake, and the mission is what got bolted on. The architecture has 2 stages. The first accelerates the whole assembly to 1/10 of light speed. Then it lets go and makes a small sideways burn. It flies past Alpha Centauri A and B forever, gathering what it can on the way through. The second stage exists for exactly one purpose: It stops about 10 kilograms of scientific payload at Proxima Centauri and puts it in orbit around the planet. 10 kilograms is about a very large house cat. Here's the mechanism, and it's a strange one. We store antiprotons on board. We release them, a few at a time, into a thin sheet of depleted uranium, the leftover material from enriching reactor fuel. An antiproton that stops inside a uranium nucleus annihilates. The particles that come out get absorbed by the nucleus, and the nucleus splits. Roughly 98% of antiprotons that stop inside uranium cause fission. Fission throws off two fragments, back to back, with equal and opposite momentum. One flies into a carbon sail mounted behind the sheet and is absorbed, handing over its momentum. The other escapes out the front. What's left is net thrust, and about a tenth of the annihilation energy ends up as push. So this isn't burning antimatter as a fuel. The uranium supplies the energy. The antimatter is the spark plug. That distinction is the only reason the numbers come out anywhere near sane. They still don't come out small.
To stop a 10-kilogram package arriving at 2% of light speed and put it in orbit at Proxima, Jackson calculates 35 grams of antimatter, about the weight of a slice of bread. The mission that goes with it takes roughly 200 years. Now ask for a mission we might live to see. Raise the cruise to a tenth of light speed and the trip drops to 56 years. The antimatter requirement rises to 590 grams, a little over a pound, about a can of soup. Look at the shape of those two numbers. 5 times the speed, 17 times the antimatter. It's the squaring again, wearing a different coat, and it follows us to the end of this. There's a piece of this design that stays with you. It's the only part of tonight where somebody solved a problem instead of running into one. Both stages carry about 1,000-gram scale chips, the same sort of thing Starship imagined.
As the ship crosses the outer solar system, and then the empty gap, it fires them off sideways, one at a time. Each one makes a close pass of an object nobody has ever seen. Roughly one flyby a week, for decades, all the way out. The laser it uses to spot those targets doubles as the radio home and as the thing that recharges the chips. That's the reward for being able to stop. Not one photograph. Decades of them, and a working spacecraft at the far end still taking more. And once it's in orbit, the same laser turns downward. Pick the wavelength carefully, and it maps the surface of the planet through cloud, the way we map Venus with radar. A world we currently know as a wobble in a spectrum would become a place with coastlines, if it has any. And now you can see why the amounts are so small. When a gram of antimatter meets a gram of ordinary matter, the pair vanish completely and turn into energy. All of it. Nothing else in nature does that.
1 gram against 1 gram releases roughly the energy of 40,000 tons of explosive. A pound of this stuff is a serious fraction of a year of a country's electricity, folded into something that would fit in your hand. So can we make a pound of antimatter? At its peak, Fermilab produced about 2 nanograms a year. CERN's output is roughly 100 times smaller than that. 2 nanograms comes to this. A single grain of table salt weighs about 60 micrograms. Accumulating 1 grain of salt's worth of antimatter at Fermilab's best rate would take about 30,000 years. For 590 grams, at that rate, we'd need something close to 300 million years. Longer than there have been dinosaurs. Jackson knows this, and his proposal includes a fix. He's designed a specialized collider that could produce 20 grams a year. The electricity alone would run about $670 million annually.
At that rate, 590 grams takes 30 years of a dedicated factory running flat out, doing nothing else, for one spacecraft's brakes. And then it has to be held. Where do we keep a pound of antimatter for 56 years? What holds it off the walls? What happens if the trap loses power for 1 second in year 40 with nobody aboard to notice? What happens to the ship when it does? Nobody has an answer that runs longer than about 16 minutes. That's roughly the record for holding trapped anti-hydrogen in a laboratory on the ground with a team watching it. Jackson's own summary of where this leaves us is the most honest sentence anyone in the field has written. He puts magnetic braking in the impossible category. He puts antimatter in the merely improbable one. And he argues that the gap between impossible and improbable is exactly the gap worth spending a career on. Every laboratory that has ever made antimatter, across the whole history of our species, has produced a total you could not see without a microscope. The break needs a little over a pound of it, and nobody has ever held any of it for longer than it takes to boil a pot of water. And not one of the 10 schemes we've walked through tonight has had to carry a person. Let's consider the crew's perspective, because everything changes when there's a body aboard. It changes in ways that aren't obvious. Start with the gentlest possible braking. 1 gravity. Exactly what you feel sitting in your chair right now, applied backward, steadily. Shedding a fifth of light speed at 1 gravity takes 71 days. 10 weeks of deceleration, which sounds almost pleasant. Now look at the runway. At that rate, you cover about 1,200 astronomical units while slowing down. Voyager 1, after half a century of flight, is around 170. The crew starts braking roughly 7 times farther out than our most distant machine has managed since 1977. At that distance, the destination star is a bright dot. Not a disk, a dot. The crew fires the burn that decides everything, aimed at something they cannot yet resolve, and then holds it for 10 weeks. Coming in slower helps, but less than you'd hope. From a tenth of light speed, the burn takes about 5 weeks and eats 300 astronomical units. Still outside the whole planetary system, still aimed at a point of light. So shorten the runway by braking harder. This is where the body enters the arithmetic. At 2 gravities, the numbers halve. And at 2 gravities, you weigh twice what you weigh now. Lying flat in a bunk for 5 straight weeks. Your chest weighs twice as much every time you take a breath. Your heart pushes blood up a column that's suddenly twice as heavy. Standing up would be like standing up with another adult on your shoulders and staying there. Nobody has ever tested that. Centrifuge runs at 2 gravities, last hours, not weeks, and volunteers come out unsteady. The longest anyone has stayed in space continuously is about 14 months, in free fall, which is the opposite problem. On what a month of doubled weight does to bone, to eyes, to the fluid around the brain, nobody has any data at all. And that's the easy version. The largest crude design anyone has published came out of a competition that closed in 2025. The winning entry is called Chrysalis, and it's the most detailed generation ship ever put on paper. It's 36 miles long. You could not walk the length of it in a day. It masses about 2.4 billion tons, close to the weight of every car on Earth put together. Inside are nested rotating shells, spinning for gravity, carrying farms and workshops and homes for about 2,400 people. A small town. It cruises at roughly 1% of light speed. 1 year of acceleration, 4 centuries of coasting, 1 year of braking. 4 centuries, 12 or 13 generations. The design team proposed something else to go with it, and it's the strangest detail in the document. Before launch, the crew and their descendants would live in Antarctica for 70 or 80 years, learning how to be a society that cannot leave. There's a geometry problem hiding in a ship like that, and people forget it constantly. A vessel that spins for gravity has one down. A vessel that brakes has a different one. Spin pushes you outward, toward the hull. A braking burn pushes you along the axis, toward the front. During the burn years, the floor is in 2 places at once, and neither one is where anybody grew up expecting it. Chrysalis handles the structural side by being a long, narrow cylinder, which keeps the stresses manageable. That doesn't make the sensation manageable. A generation raised with one direction of down spends its final year learning a second one. Now here's the part about the brakes. In world ship studies, the shielding runs over 90% of the vehicle's mass. Most of a Starship isn't engine or habitat, it's wall. You need it because at even 1% of light speed, the interstellar medium is a slow, endless sandblast, and the cosmic rays never stop. One proposal solves 2 problems at once. Use the deceleration propellant as the shield. Deuterium stops radiation about as well as anything else you'd haul, and thousands of tons of it are aboard anyway. So put it in front. Follow that through to the end of the voyage. In the final years, the thing protecting the crew is being fed into the engines to slow them down. The closer they get to the star, the thinner the wall between their children and the radiation. They arrive at the most exposed moment of the trip, carrying the least armor they've ever had. There is no version where they get both. There's a corridor problem too, and it's narrow. Breaking into a star system isn't one number, it's a window. Come out of the burn slightly too fast, and the system lets you go. Everything after that is coasting into empty space with the tanks dry. Come out slightly too slow, in the wrong place, and the star's gravity keeps you falling inward. The margin between those two outcomes is set by a burn that started 10 weeks earlier, aimed at a dot. Then there's the aiming, and this one bothers me more than the rest. To break into orbit around a specific planet, you have to know where that planet will be on arrival. For a 20-year crossing, the prediction has to run about 25 years ahead, because the light it's built on is also 4 years old. For Proxima Centauri b, that's 831 of its years. It can't be done. The position of that planet along its orbit is undetermined more than about a year and a half out. Fixing that would need a parallax measurement roughly 50 times better than the best catalog in existence. And relativity gives no relief. People assume the crew gets the trip for free through time dilation. At a fifth of light speed, shipboard clocks run about 2% slow. Over 20 years, that's 5 months. Dilation only turns generous close to light speed, and every step closer makes the break worse. The one effect that would shorten the voyage for the crew is the same one that makes stopping impossible. Then the signal delay. 4¼ years out, 4¼ years back. A question asked during the braking burn gets answered by people who weren't in the room, in a language that has drifted. About a decision made 9 years earlier by someone probably dead. Nobody aboard can ask for help either. The burn is autonomous by necessity. The ship makes the call, and the ship has to be right the first time. Nobody who authorizes that burn will ever hear whether it worked. And there's a question hanging over a 4th-century ship that the engineering documents can't answer. Who decides to stop? The people who chose that star died 12 generations back. The people at the controls were born in flight, and so were their parents, and their parents. They have never stood on a planet. The place their ancestors picked out is a rumor they were raised on, arriving as a dot in a window. They might not want to go down. A society that has spent 400 years learning to live inside a cylinder may have opinions about a world with weather on it. The braking burn is the moment a plan made by strangers becomes an order given to their descendants. Nobody has worked out who has the standing to give it. Would you go? But this raises the obvious question, and it's the one that closes the circle. Why not build the brake in advance, at the far end? Braking scheme number 9. Send the infrastructure first. It isn't a silly idea. If the problem is that the brake has to be carried, then don't carry it. Put it out there ahead of time, waiting, and arrive into a system that already has hardware in it. One published version does the arithmetic all the way down, and the number at the end sticks with you. The scheme sends a fleet of tenders ahead of the probe. Each one stages fuel pellets into position along the approach path. The probe then flies into a prepared corridor of ammunition and eats it on the way in. The catch is that every tender has to be slowed down too, below the speed of the thing it's feeding, which takes another tender, which takes another. For a cruise at a fifth of light speed, the chain runs 6 stages deep, 21 tenders, to bring one probe to rest. The related idea, the pellet stream, has been around since 1980. Fire a river of gram-sized pellets at a large sail and let momentum do the rest. It's elegant for acceleration. It was abandoned for deceleration for a reason that should sound familiar. You cannot aim the stream from the wrong end, and a flyby can't quietly drop the hardware off on its way past either. Anything released from a probe moving at a fifth of light speed is also moving at a fifth of light speed. Letting go of a package doesn't slow the package down. There is no way to hand something to a star as you go by. And here is the one number in this subject that sticks. Current swarm designs do use interstellar drag on purpose, not to stop, to steer. Turn a sail face on to the oncoming medium, and it decelerates at about 4/1000 of a meter per second squared. Drop a coin under a pull that weak, and it would take 20 seconds to reach the floor. That tiny force is useful. It's enough to slow the later probes until the earlier ones catch up. Over a couple of years, it assembles 1,000 scattered machines into a formation. Turn the sail edge on instead, and the drag falls by a factor of 50. The medium can steer a probe. Can it stop one? At 4/1,000ths of a meter per second squared, shedding a fifth of light speed takes roughly 5 centuries. And that's the optimistic figure, with the sail held flat into the wind the entire time. Which we cannot do, because holding anything face on is what destroys it. Over the crossing, dust strips away about 0.5 millimeter of surface, roughly the thickness of your fingernail. On an exposed rim, a dust grain hits every 3 seconds, each carrying about the energy of a teaspoon of sugar falling off a shelf. Instruments turned forward aren't expected to last more than a few months. There's a one-way sign on the whole thing as well. The medium can only ever slow you. You can't push off it to go faster. It's a brake that doesn't work, and a road you can't drive on. There is one serious attempt to break the circle, and it's the only one anybody has ever made. Send machines that build. In 1980, an engineer named Robert Freitas worked out what it would take to turn the Daedalus design into something self-replicating. His answer was a seed factory of about 440 tons. Delivered to a target system, it would mine local material and construct copies of itself, and then construct everything else that was needed. There's the escape hatch. Don't ship the laser, ship the thing that makes lasers. Now read that sentence again. Delivered to a target system. The seed has to stop. The first machine that arrives and stays still has to carry its own brake, unaided, exactly as before. Self-replication doesn't solve the arrival problem. It solves everything after the arrival problem, which is a different thing, and only useful once. Which brings us to where the evening was always going. Every scheme that fully closes the arithmetic needs something already in place at the destination. A laser, a mirror, a fuel depot, a tender fleet, a receiver, a factory. Something built, positioned, and waiting. The only way to put something in place at another star is to send something that stops there. Every complete answer assumes its own conclusion. That is the shape of it. That's why stopping is harder than going, and it was never really about the equation. Going happens where we live. A launch is surrounded by a planet, factories, power grids, a workforce, spare parts, a whole civilization standing behind the push. If the first attempt fails, there's another next year. Arriving happens where there is nothing. No workshop, no second attempt, no one to ask. The entire industrial capacity available at the far end of the journey is whatever got bolted onto the ship before it left. The engine can stay home. That's the whole trick, and it's a good one. The brake cannot. Only one plan we've looked at tonight escapes this. It escapes by making the destination star itself the infrastructure, braking on light that was already there. It pays for that with 140 years, and a hard ceiling on how fast it can ever arrive. Which leaves exactly one thing left to trade. We need to talk about the variable nobody wants to touch. Every scheme tonight has treated speed as fixed. Get there in decades, that's the requirement. Now solve the brake. Under that requirement, nothing works. So turn it around. We should ask instead how fast we can go and still be able to stop. Because the brakes do work. They've always worked. They work beautifully at a 300th of the speed of light. Here are the numbers that close, from the same simulations that broke the magnetic sail at higher speeds. A craft weighing about 1.5 tons, roughly a family car. A superconducting loop, 29 miles in radius. The interstellar medium brings that to a complete stop on its own. No propellant, no beam, no infrastructure at the far end. And it works even in the emptiest local stretches, where a sugar cube of space holds 1/20th of an atom. Better still, the launch requirements fit inside the same laser array that was being designed for the fast probes. The same hardware that throws a gram at 1/5 of light speed can throw a car at 1/300th of it. Nothing new would have to be built. We'd only have to want something different. And look at what else goes away when the speed comes down. At 1/300th of light speed, a dust grain arrives with a tiny fraction of the energy it carries at a fifth. The erosion stops being a design driver. The shield gets thin. The heat load on the leading edge stops mattering. The electronics are no longer sitting in a hydrogen beam for 20 years. Notice that on its own. Almost every hard problem in interstellar flight turns out to be a problem with speed, not with distance. Distance costs patience. Speed costs everything else. Here's what the patience actually comes to. At that speed, reaching the 7 planets of the TRAPPIST-1 system, about 40 light-years out, takes 12,000 years. 12,000 years is longer than agriculture. Everything our species has written down fits inside that span with room left over. Every language we can still read, every building we've kept standing. The people who launch it sit upstream of the arrival by a distance nothing human has ever crossed. Their nation, their alphabet, their idea of what a person is for. The mission changes. It stops being exploration because there's nobody left to explore for. The version actually proposed is called seeding. We don't send instruments, we send life. Single-celled organisms, carried to a world that has water and warmth, but never started anything on its own, and released there to begin. No return. No data in any sense that helps us. Nobody on either end who could hear from the other. The payoff, if there is one, is not on any scale we use. A seeded world wouldn't have anything worth looking at for hundreds of millions of years. Our own planet took roughly that long to get past single cells. The mission would be finished, in the sense that matters, long after the sun has changed and the launching species has become whatever comes next. There's a question underneath that nobody has settled. If a planet has water and warmth and nothing alive on it, is that an empty lot or is that a place? The decision would be made on behalf of everyone downstream, and we would never learn what we'd done. That's the deal on the table. We can stop, or we can arrive inside a human lifetime. Not both. And the version that stops asks us to spend everything and be told nothing. That isn't a solution. It's an honest description of a choice, which is rarer and in some ways worse. There's a quieter middle path some people are sketching, and it deserves a mention because it's the only near-term answer that isn't a compromise. Don't go to another star at all. Go about 550 astronomical units out, where our own sun's gravity bends and focuses the light of distant planets into a point. Park a telescope in that focus. It isn't a rival. Nobody touches anything. But it's the one version of this where the people who launched the mission are alive when the pictures come back. Now, let's come back to what's still missing. It isn't a short list, and parts of it are more open than the confident diagrams suggest. We don't know whether a magnetic sail works at all at relativistic speed, not whether it's efficient, whether it functions. The field has to be strong enough to turn protons inside the thickness of the shock it creates. The shock also has to stand off far enough to form. In the simulations, those two conditions are only marginally compatible, and the available models can't resolve which way it falls. Settling it needs plasma calculations nobody has run. We don't know whether any material survives both ends of the trip. The sail takes 40,000 gravities leaving. It takes a stellar corona arriving. In between, 20 years of hydrogen at a fifth of light speed. Nobody has built a sample that has survived even one of those three. We don't know whether antimatter can be produced or held in useful amounts. Production is short by a factor with 9 zeros in it. The storage record is minutes. We don't know where the target is. The uncertainty in the planet's position is about 20 times larger than a mission can tolerate. We'd be launching at a moving object whose future we can predict for a fraction of 1% of the flight time. We don't know how to navigate once we're out there either. Pulsar timing is the obvious answer, and inside the solar system, it works to within a few miles. But the distances to the pulsars themselves are uncertain by light years. Move a few light years sideways and their apparent positions shift, which ruins the timing. The first interstellar mission would have to measure those distances properly so the second one could steer. We don't know whether the machine stays alive. A gram-scale probe runs on a nuclear battery putting out around 9 milliwatts at launch, decaying to 6 by arrival. That's less than a hearing aid draws. Every transistor aboard has to survive 20 years of cosmic rays with no technician, no reboot from the ground, no spare. and we don't know how to decide what comes back. The swarm records more in 1 minute than it can transmit in years. Somebody has to write, in advance, the rules by which a machine 4 light-years away chooses which picture of another world matters. Nobody has written those rules. Nobody is certain they can be written. And nobody has ever properly compared the prize with the alternative. A stopped probe gets decades at a planet, but a large enough telescope, parked in the right place, could stare at the same planet for months at a time. Forever. And it would be built by people who see the results. One astrophysicist, looking at the early flyby plans, said the telescope would return more. That comparison has never been run properly for a braking mission. It is the first thing anyone spending a century of a civilization's effort ought to want. Then the structural one, which is the reason for tonight. Nobody has proposed anything that avoids all 3 costs at once. The squared mass, the infrastructure at the far end, the centuries. Every scheme on the table pays at least one of them. The ones that look cheapest are the ones examined least. The teams doing this work know it, and that deserves saying. The Dragonfly group wrote down that their own braking design might not be worth flying. The antimatter proposal calls itself improbable rather than impossible, and treats that as the achievement. These aren't dreamers who never ran the numbers. They're the people who ran them. The distance is settled, the speed is achievable, the arrival is not. We know how to build the engine. We know how to build the beam. We know how to build the sail. We do not know how to build the brake. We know how to leave. We know how to cross. We do not know how to arrive. And yet the way we found all of that out deserves a moment. Nobody learned this by failing. There was no crash, no lost crew, no wreck burning at the edge of another star system. It came from arithmetic done on paper, decades before anyone could attempt the trip. Then from people checking each other's arithmetic until the comfortable answers fell apart. A rock thrown into space keeps going. A rock cannot know that. Something that became alive learned to change direction. Something that became conscious learned to ask where it was heading. And something that became honest learned to work out in advance that it could not get there. Then to say so out loud, while the funding was still on the table. None of which slows anything down. The equation still squares. The space between the stars is still almost perfectly empty. The first thing we send will still cross another star system in a flash and keep going. Everyone who built it will be gone before the answer comes home. Thank you for joining me on this journey through the arithmetic of arriving, through mass ratios and mirrors, through sails 1/5 of a mile wide and coils 1,000 miles across, through a long line of clever people finding out, one at a time, that the hard part was never the going. If you'd like more nights like this one, subscribing and leaving a like helps the channel reach people who think about these things too. And the next time somebody tells you we're 20 years from another star, remember what that first machine will do when it gets there. It will see the place for less than a minute. Then it will go out the far side into the dark, still moving at 1/5 the speed of light, forever. Good night, and may everything you're traveling toward be something you can stop for.